Okay, welcome everyone to the colloquium. Today we're happy to have Florian Herzig from the University of Toronto who will speak, who will give us an introduction to the multi-Langlands program.
Thank you very much. I thank the organizers for inviting me to visit Herzig and Pohang for the first time in my life. It's a pleasure to be here. And yes, so I will try to give an introduction to the Mod P Langlands program. So I will not assume you know what the Langlands program is about. And I want to start really from historical beginnings, like the ancient questions that interested mathematicians in number theory. So I want to start with the question of squares modulo primes, which goes back to ancient times, I think. So the first problem is how many solutions does a quadratic equation have modulo a prime number p? So for example, x squared minus 3. For any, it's not hard to see. So this is kind of, you might learn about that in undergraduate number theory. So you either have usually 0 or 2 solutions, or exceptionally you can have 1 solution. So let me give examples. So modulo 11, we can see that there are 2 solutions because 5 squared is 3 modulo 11, has remainder 3 when we divide it by 11. And same for negative 5 then. But for other prime numbers, we get 0 solutions. For example, for 5, we can just try all the numbers modulo 5, square them, and we see we never get 3. And then an exceptional situation happens when we take the prime 3. There's precisely 1 solution because 3 is 0. Plus or minus 0 is 0. So this was already, this particular equation was solved by Pierre de Fermat in the 17th century. And he found that there's a simple answer to this problem, namely, there are 2 solutions precisely. So he gave precise congruence conditions for when these cases happen. And it only matters what the prime is modulo 12. When it's plus or minus 1, you get 2 solutions, etc. So he found a complete solution for this particular equation. And then later, so over the next 100 or so years, mathematicians continued to study this problem of squares modulo squares or square roots modulo primes. And Gauss was, I believe, the first one to prove that there's this general, I think he proved something that was conjectured before, that that this is a general phenomenon. Whenever you want to solve the question of squares modulo p, the answer only depends on p modulo some integer, some other integer, which is something that's completely unclear from the beginning. Like here, when we look at this problem, it's not clear at all that there will be a simple recipe that only depends on p modulo something else. And the something else it depends on is 4n. So in the previous case, it was 3 and 12. And that is his amazing quadratic reciprocity law. And Gauss was very fascinated by that there's this funny relationship between what the squares are modulo p and what p is modulo something else. And so I think that was the reason why he kept finding new proofs for his quadratic reciprocity law. I think he proved it 8 times in his lifetime. And you can find whole books that contain different proofs of this. But still, there's something magical about it. And this is just the beginning of a much bigger story. So the next case, which looks very different from the surface, is that of elliptic curves. So I want to switch gears and look at cubic equations in 2 variables. For example, this one, y squared plus y is x cubed minus x squared. And again, I want to look at the number of solutions, not of the equation itself, but modulo a prime number, and then see what happens when I vary the prime number p. So I let np denote the number of solutions modulo p, the number of pairs x comma y that satisfy this equation as a congruence modulo p. And it's easy to count for small primes p, and I tabulated the result here. It just looks, it doesn't seem to be much structure, like if I look at it. But the first interesting observation, I think, was made by Hasse in the 1930s to show that actually these numbers are close to P. They don't differ too much from P. And the error, in fact, he could show is at most 2 times the square root of P. So if we take that difference, you can see we get numbers that stay pretty small compared to P. And by the way, P would be the number of equations on a line. And here we have a more complicated curve in 2-dimensional space. So it's maybe not completely unreasonable to take the difference with P, the number of points on a straight line. Maybe it stopped working.
Yeah.
Is it the battery?
I'm not sure. You use these 2 buttons, or I'll try to press this.
Oh, I see. Okay.
Give me 1 second.
Right. So once again, I write down the same people at the top. And 20 years later, Martin Eichler, he realized that these numbers are connected with a completely different kind of object, a modular form. So the particular modular form it's related to is given by this strange infinite product of q times this combinatorial looking object, q times the product of 1 minus q to the n squared and 1 minus q to the 11n squared. You get this infinite series in powers of q, and the coefficients that matter here are the ones that are before the q to some prime exponent, q squared, q to the 5, q to the 7, and so on, q to the 3, q to the 5, q to the 7, q to the 11, and so on. And those are exactly the same coefficients we saw up there. So this is maybe not the most classical way to look at these modular forms, but rather we change variables and let q, this variable in the power series, be e to the 2 pi I times complex variable tau, which lies in the complex upper half plane. And then this function, after this change of variables, this function becomes a holomorphic, so the complex differentiable function on the upper half plane in the complex numbers. And that has a very remarkable symmetry property. Namely, whenever I plug in, whenever I take a transformation of the variable tau by a fractional linear transformation, a tau plus b over c tau plus d, where the a, b, c, d are lying in a certain subgroup of 2 by 2 integer matrices, namely where c is divisible by 11, then we get almost the same function back, except there's a normalizing factor. But essentially, we get a function, if you ignore maybe this normalizing factor, we get a function that has very large symmetries by this group Sn2Z or some finite index subgroup of it. So this is an example of a modular form. And modular forms, so they're governed by, it has to do with the action of this group Sn2Z by Möbius transformations on the complex upper half plane. So if you want, this is a very different kind of object than the one we started with, the elliptic curve. So here we have an object of complex analysis that has been studied that was studied a long time before Eichler noticed this connection to elliptic curves. Yes. Yes.
Okay.
Oh, great.
These 2.
And
This
then,
one.
yes, thank you. Okay, so this is my second instance of reciprocity that will lead us towards Langlands program. So one way of saying what reciprocity is about, it's about finding a law that governs how many solutions a polynomial equation, maybe in many variables, has when we reduce it modulo a prime p and let the prime p vary. So just like in the previous two problems, but now a completely general kind of polynomial, or maybe even a system of polynomials in several variables. And then Artin around 1930, he proved a huge generalization of Gauss's law of quadratic reciprocity, but it only applied to very special kind of instances of this problem. So this is what's called class field theory. And I will say a bit more about that soon. And then after that came Langlands much later, and he wanted to propose a completely sort of general framework for answering, for providing solutions to this general reciprocity problem. Any questions so far? So I give two particular instances of this reciprocity problem to motivate it in general. So now to go back to sort of the beginning of squares modulo primes, Gauss realized that there's a connection of the quadratic equation you want to solve, x squared minus n is 0 mod p. He realized it's related to the cyclotomic equation x to the p minus 1 is 0. So here, the solutions of this equation in the complex numbers are just pth roots of unity. They are powers of e to the 2 pi I divided by p. When p is 5, I drew the picture here. Those are the 5 solutions of this cyclotomic equation in the complex plane. And now I want to explain a little bit why there's this connection. So first of all, so I remind you zeta p is this pth root of unity, this complex number whose pth power is equal to 1. And it generates a field, so a domain of the complex numbers that's closed under addition, multiplication, and division by non-zero numbers that contains all the rational numbers, q, and also this pth root of unity, zeta p. And it's not hard to check that you get precisely all polynomial expressions in zeta p with rational coefficients. And this field has a lot of symmetries. So this is so the symmetries of a field is what was studied by Galois that was studied by Galois, and he, well, maybe Gauss together with Galois realized that the symmetry group of this field of pth roots of generated by pth root of unity is precisely the same as the units, the multiplicative units in modular arithmetic modulo p in Z mod pz. And the isomorphism is completely explicit, so the residue k in Z mod pz corresponds to raising the pth root of unity to the kth power. And correspondingly, any expression in that field, once you send zeta p somewhere, you know where every other element goes because the operation has to be compatible with addition and multiplication. So this gives, so this classifies, this isomorphism gives you the classification of all the symmetries of this field of pth roots of unity. And then now let's look at the problem of squares modulo p. For each residue A modulo p, I can send that to plus or minus 1, depending on whether A is a square or not, modulo p. And I ignore 0. 0 is the one exceptional value. I just look at non-zero values modulo p. And this so-called Legendre symbol is multiplicative. So if A and B are both squares, then AB is also a square. If one of them is a square and the other isn't, then the product is also isn't, and so on. So we get the homomorphism property that AB over P is, or chi AB is chi A times chi B. And because of this isomorphism on top, we have these two groups that are the same. We can think of this homomorphism as a homomorphism of the Galois group. So we get a homomorphism of the Galois group up here in the start equation of Q zeta P over Q to plus or minus 1. And even though it seemed we didn't do anything complicated, this is actually giving us a new information or a new insight into this problem, because the kernel of this homomorphism, the elements that are sent to 1, half the elements are sent to 1 and half are sent to -1. And the elements that are sent to 1 form a subgroup in this Galois group, which by Galois theory determine a quadratic extension lying between Q and Q zeta P. And already Gauss knew what this was, because he knew how to get a square root of P, or maybe negative P, using the p roots of unity. So it's either Q adjoin the square root of positive P or negative P, depending on whether P is 1 or 3 modulo 4. So there's a precise answer what this quadratic intermediate field is. And using that, it's then not so hard to give a proof of quadratic reciprocity. So that's one possible. This is at least motivating one particular proof you can give of quadratic reciprocity. And this is a first example of a so-called Galois representation, of which you will see more in the remainder of the talk. So I wanted to explain this in the simplest case, that there's this connection between something that does some concrete group like Z mod P cross and a Galois group, and this turns out to be useful already in this example. So now I need to explain maybe 2 more things before I talk about some more general questions in the Langlands program. And I hope I'm not going too fast. Please feel free to stop me at any time. So the next thing I want to explain is p-adic numbers. So I'm not assuming you're familiar with them. Not everybody learns about p-adic numbers. So these were first introduced more than 100 years ago by Kurt Hensel, and they're obtained in the same way that you obtain the real numbers from the rationals, by instead using an unusual absolute value. To get the reals from the rationals, we use the usual absolute value on Q. But for the p-adic numbers, we take an absolute value for which P is small, or powers of P are progressively smaller. So more precisely, the definition is here. We just look at the largest power of P contained in a rational number, and depending on how big that power is, the smaller the absolute value will be. So it's just a bit counterintuitive, perhaps, but this satisfies all the usual properties of an absolute value. And in fact, it's better than that. It's not just an absolute value in the sense of metric spaces, but it satisfies a stronger form of the triangle inequality, namely that x plus y is less than or equal to the maximum of absolute value of x and absolute value of y, which is itself less than or equal to the sum of x and y. But this stronger version of the triangle inequality means that everything becomes easier than for the real numbers. For example, just to give one example, a series converges now if and only if the ith term goes to 0. We know in real analysis the implication only goes one way, but now the nice thing is here it goes both ways, which makes analysis much easier. And for example, what we can then see is that every element of the completion in QP So the completion is obtained the same way as for the reals, but every element in QP is uniquely expressible as a convergent power series in P. So it can be written as some AI P to the I, where the coefficients lie between 0 and P minus 1. And I greater or much greater than negative infinity means it has to start at some not too negative point. The series can start at negative 100 or at negative 1,000, it doesn't matter, but it has to start somewhere. It cannot be arbitrarily negative. The problem would be that the negative powers of P get larger and larger and larger in this metric. So we have to start at some point, not arbitrarily negative. And here's one particular example of analysis happening, taking sort of the binomial series now converges, at least as long here as n is not divisible by p. We can take an nth root of 1 plus p by using the binomial series. It converges because p to the I goes to 0, and the binomial coefficient is still p integral. It doesn't have any p's in the denominator because of the condition on n. So I'm trying to convince you that p-adic numbers are a very analogous thing to the real numbers, but they're also much easier in a way. Analysis becomes easy, and also algebraically it's easier. For example, we can write down a general element in a canonical way, whereas for the reals, it's a bit more hairy. So I remind you here, this is QP, and then the p-adic integers are the elements that we obtain by approximating actual integers rather than arbitrary rational numbers. Or equivalently, we only start this series up there at I equals 0. We do not allow any negative powers of p. And this ring of integers also is a little bit like the integers. Well, it's uncountable, but in some ways it's simpler than the integers because it's compact. The topology is compact now. QP is only locally compact, but ZP is compact. P is the only prime element. In Z, we have infinitely many primes to worry about. One reason why p-adic numbers were invented and are used is because we can narrow down on one particular prime without having. One reason why Q and Z are so complicated in number theory is because we have all these different prime numbers to worry about. And the last good property I want to mention is that giving a p-adic integer in ZP is really the same as giving a compatible system of congruences for all powers of p. Like, I know what it is mod p, I know what it is mod p squared, I know what it is mod p cubed, and so on. So any such congruence uniquely gives me a p-adic integer, just because of how ZP is defined. So these are the p-adic integers, and so now there's a second thing I want to talk about in the context of elliptic curves, namely, I talked about this the first appearance of Galois theory in the context of cyclotomic fields. So here will be the second appearance of Galois theory in the context of the elliptic curves modular form story. And again, please feel free to interrupt. I hope I'm not going too fast. If you ask a question, you will slow me down more. Any question about anything so far? P-adic numbers or reciprocity or anything else I mentioned so far?
Well educated here.
Sorry?
Students are well educated.
Okay, that's great. Then save your questions for the more deeper parts later, I guess. Okay. Well, also I didn't know I didn't want to assume anyone is like in number theory or algebra, so I'm trying to keep it broad for the moment. So next I want to talk about the connection with Galois representations with Galois symmetries in the context of elliptic curves. So let's go back to the elliptic curve I had some time ago, y squared plus y equals x cubed minus x squared. And then instead of counting over z mod pz, I can also now look at this elliptic curve with entries in Q, or maybe even in the algebraic closure of Q. In that case, it is actually much more natural not to look at this affine equation, sort of in the two-dimensional plane, but to also add a point at infinity and think about it in projective geometry, so in kind of two-dimensional projective space, by making the equation homogeneous. And then one great thing about the elliptic curve, one very special thing among curves, is that it's not just a curve, a sort of one-dimensional geometric object, but it also has a group structure, an abelian group structure, where our chosen point at infinity, which I denote by O, is the identity of that group law. So here's a quick summary of how that works. So that's a classical construction in projective geometry that's been known for hundreds of years. So the nice thing about this is a cubic curve. We have degree 3 polynomial. The nice thing in projective geometry is whenever we intersect the cubic curve with a line, and we count with multiplicities, we always get an intersection. We always intersect 3 times exactly. So here the picture is we start with P and Q. If we now want to add them in the group law of the elliptic curve, I have to connect P and Q, take the third intersection point of the cubic curve with the line. This doesn't have a name here. And then I connect this third intersection point with the point at infinity. So that kind of means I should take a vertical line going through that point, and I get the third intersection point. So the point at infinity is the second one, and the third one is the reflected one down here. And this one is the sum of the 2 points in the group law of the elliptic curve. So it's a very concrete operation. I mean, I'm cheating slightly because this is the real picture of the elliptic curve. You would have to do that in a complex picture to really always have 3 intersection points. But the takeaway is the elliptic curve has this great extra structure of having an abelian group operation. And since we have an abelian group, we can look at points in the elliptic curve that are M torsion points. M torsion means that if we sum them up M times in the group law, we get the identity. We get the point at infinity. And it is known, it's not so hard to see that the structure of this, first of all, it's a finite group that we get something finite, and it has exactly M squared elements. And as an abelian group, it's a direct product of 2 cyclic groups over the M. And if we really, so now it becomes important that we take points, not just in the rational numbers, but in the algebraic closure. A priori, we could maybe take the complex numbers so far, but now I want to use the symmetries. I want to use the Galois symmetries, and for that reason, I only look at algebraic points. I only input algebraic numbers, not arbitrary complex numbers, into the elliptic curve equation, and then I get an action of the Galois group. So any symmetry of the field of algebraic numbers will give me a symmetry of these M torsion points. And concretely, what one obtains is, so we get an action of the Galois group on this finite abelian group, which I can write down as a homomorphism from the Galois group, from this absolute Galois group, to the automorphisms of the M torsion group. And these automorphisms are just like 2 by 2 invertible matrices over Z mod MZ. So this works for any positive integer M. But the ones I want to take, in the spirit of the p-adic numbers that I talked about just a moment ago, I want to take M to be powers of some fixed prime. And then I can go from compatible congruences to p-adic, or in this case, L-adic integers. And just focus on that one prime. I don't want to worry about all primes at the same time. I just want to focus on one prime L. I fix one prime L, and I package all of these Galois representations or homomorphisms together. It's very easy to see that if we take increasing powers of L, they're all compatible with each other. And so I get a homomorphism just as before, but now valued in GL2 of the L-adic integers, so that when I reduce it modulo any fixed power of L, I get the homomorphism back that was in the previous line. So I package all of them together for all the ones that are a power of a fixed prime L. And these are called L-adic Galois representations. So these appear in algebraic geometry, in arithmetic geometry, and in number theory, and in the Langlands program. So my first example of a Galois representation, which was a one-dimensional one, was this isomorphism of Gauss, maybe of the Galois group of the cyclotomic field with Z mod P cross. Z mod P cross is GL1 of Z mod PZ, and here we now have GL2. So these are kind of the special cases of the Langlands program that I want to talk about. So here is a little bit about the picture. So on the one hand, we have Galois objects. So we had the one-dimensional representation, even just going to plus or minus 1, of the Galois group of the cyclotomic field. And we had the two-dimensional representation coming from the elliptic curve. On the other side, what we saw on the so-called modular world, because we see modular forms, so that modular forms appeared in the context of elliptic curves, and these sort of Legendre symbol characters appeared, or Dirichlet characters appeared in the context of cyclotomic fields or quadratic reciprocity. So both of these particular cases that I discussed are instances of the Langlands program, of a Langlands correspondence, which is an extremely rich, complicated, elaborate story that I can only touch upon in this talk. But just to orient yourself, I want to say that, I mean, this first case had to do with quadratic reciprocity and these much more general reciprocity laws that led to Artin's reciprocity in 1930 in the context of class field theory. And then the second kind for elliptic curves and modular forms is what led to Fermat's last theorem and actually more generally the Shimura-Taniyama conjecture that specifically asked about the connection between elliptic curves and modular forms over the rational numbers. And these were established by, Wiles, Taylor-Wiles in the 1990s, and then in complete generality for the Shimura-Taniyama conjecture by Breuil, Conrad Diamond, and Taylor in 2001, roughly. So there's a very, so Langlands has these very, very general conjectures. Only certain things are known, but even the known cases lead to extremely rich arithmetic applications. And also just general deep connections between a priori unexpected fields and problems. So the Langlands program has been, very, I mean, sometimes maybe people have used very grand names like grand unified theory of mathematics or something like that. I don't subscribe to that, but it is a very big framework to think about lots of different areas or kinds of problems and objects in mathematics. Okay, so next I want to talk about Yes, so now I want to go from this more general, what's also called global Langlands correspondence to the title of my talk, to mod P and p-adic Langlands correspondences. And the first step is to go from the global correspondence to a local correspondence. So what happens is we have this reciprocity between, let's say, elliptic curve and modular form, or the corresponding Galois object and the modular form. But just like the p-adic numbers isolate one prime at a time, we can do that in that correspondence too. And for any prime number p, I can restrict from this big Galois object, big Galois representation on the left, to some much smaller kind of to the representation of this much smaller subgroup. That's the Galois symmetries of the p-adic numbers and its algebraic extensions. Whereas here we have the symmetries of the algebraic numbers, and this is a much bigger and much richer object. Here, just kind of focus on that one particular prime p. Maybe you have, And in the same vein, so here I take res means restriction. I can restrict from this very, very big group, which we don't really understand in any satisfactory way, to this much smaller Galois group, which is, we get something in a way much simpler. And then similarly on the right-hand side, we have the modular form, which is this complicated, in general, object. Like it has this rich Fourier expansions, for example, that we saw at the beginning. The example at the beginning was especially nice, where it was some infinite product. In general, we don't really understand the coefficients. We only understand maybe the connection to something else, like the elliptic curve. But again, I can restrict in a certain way to something much simpler, which is even though it might look complicated on my slide, it's a representation of the p-adic group GL2QP, so the 2x2 invertible matrices over the p-adic numbers on some typically infinite dimensional vector space that I can obtain from the modular form. So trust me that this is something simpler than the modular form we started with. Because really the modular form is not the ultimate object here. There's also some much bigger representation one should perhaps consider, and this is just a small piece of that representation. And this bottom line is what contains the information at P. So in the modular forms example, this is what remembers the P minus NP, but it doesn't know about the L minus NL for the other primes L. So this is the sort of local Langlands picture on the bottom, and the global one at the top. If you're not familiar with the language, global refers to a number field like the rational numbers, and local refers to the p-adic ones. And but what's very important, and what I didn't mention yet, was that in this picture we should take the prime p not equal to L. Because, but it's very natural to ask what happens when p is equal to L. So the reason why traditionally you would not look at p equals to L is because when p is equal to L, we have a p-adic Galois group, which is a complicated p group roughly. And on the right-hand side, you have an complicated L group, like it's a generalization of a finite L power order group and the finite p power order group. It's a generalization of that. But when L is equal to p, the two sides are more compatible with each other, and we end up having a lot more representations on the left-hand side. So something new has to happen there. And it was Christoph Breuil, who after Fermat's last theorem and Shimura-Taniyama conjecture, in the context of the proof of Wiles and Breuil, Conrad, Diamond, Taylor, he was starting to wonder how you would have to modify the right-hand side of this correspondence in order to still match the much richer world of p-adic Galois representations on the left-hand side. So when L is not equal to P, we have the classical Langlands correspondence from the previous slide. When L is equal to P, something bigger seems to happen. And so Breuer was the one who kind of tried to explain conjecturally what we should put on the right-hand side. And his idea was to upgrade this and allow also a more complicated representation theory on the right-hand side. No longer representations of GL2QP on a complex vector space or a L-adic vector space, but on a p-adic vector space, where again, because the topologies are compatible, you do have a much richer world of representations. Just like when you study representations of a real Lie group, you have a lot of representations over real vector spaces. Small analogy.
So I have a question
Yes,
from the
please.
previous slide.
Yes. From this one?
Yes. So you say you can go from global to local, and the local part contains some interesting information, like for example,
Yes.
the P minus NP.
Yes.
For a specific prime P.
Yes.
But can you also go to the real?
Yes, you can also go to the
that's-
real world.
That,
That's
like
true.
what kind of number theoretic information would that contain?
So there's something, you still have a Langlands correspondence over the reals or complex numbers. That wouldn't maybe look as number theoretic as the ones that.
So it wouldn't
these.
contain any mod P information, it would contain some other type of.
Yes, it would contain some other type of information. For example, what it would contain is what sort of weight the modular form has, and yeah.
Okay.
Yes.
Thank you.
Oh, but that's a good point. From the rational numbers, we can go to p-adics for any p, or we can also go to the reals. Yes. But now I really want to go into the p-adic direction and modify the L to a P. So we can ask now, so Breuer was asking, is there some nice correspondence? So this is like what I mentioned at the bottom of the previous slide. Is there a nice correspondence between representations of a p-adic Galois group on p-adic vector spaces, and on the other side, representations of, well, it was GL2, but you can even ask this for GLN, of GLN QP on a p-adic vector space. So you can ask this for any n. And similarly, and this is a little bit simpler, but still related to the p-adic story, we can ask about it with modular coefficients. So instead of having p-adic vector spaces, we now have mod p vector spaces. So vector spaces over fp or some extension of fp. So maybe just if there are too many groups and fields floating around, just keep in mind we have like two fields always. There's the field of coefficients, so there's QP. Here we kind of conflate the two, we confuse the two, but yeah, maybe the second line is better. We have FP, the coefficients, they are the same on both sides. We have FP vector spaces on both sides. And then we have a p-adic Galois group and we have a p-adic group. So the groups are over the same fields and the coefficients are over the same. But in Langlands, I mean, in principle, you can ask for any kind of field of the group and any field of the coefficients. And that typically does seem to be an interesting story. There's also people who are interested in what happens over the complex numbers, and it goes into a much more geometric direction. Well, okay. There's an intermediate step.
One more thing,
Yes.
just to clarify. So the reps of GLN QP over QP will be smooth admissible. So that's
No. So if it's over the complex numbers or QL, then yes. But Breuer's idea was the smooth ones are not enough to explain the richness on the left-hand side. So, and now since we have compatible topologies, there are a lot more different categories of representations you can consider.
okay.
You can consider, for example, what he would like to put, for example, is Banach space representations. So they are on a complete p-adic vector space with respect to some p-adic norm.
Okay.
Yeah, so there you can talk about Banach space representations, you can talk about algebraic ones, like, finite dimensional algebraic, you can talk about smooth, which are locally constant, you can talk about maybe differentiable in different ways. There's a lot of richness, or like analytic in the sense of power series expansions. It's a bit more, this side is a bit more like representations of real groups over the real or complex numbers. You have many different types of representations you can consider. Whereas over FP, it's a bit simpler. That's also why I focus on that, partly why I focus on that story. You don't have so many different options. And here I would consider smooth, locally constant representations.
Okay.
Yeah.
And is it over FP, or do you want to take an algebraic closure?
Ideally, maybe a finite extension or an algebraic closure, but I didn't want to have too many, make it too complicated for the talk. Okay, so this is kind of the question, and this is a new type of correspondence. We know much less than in the previous slides about the classical Langlands story, where still a lot is completely unknown, but a lot more is known than in this p-adic or mod p Langlands correspondence. And even though we do not have them yet, for convenience, I will denote this by a Galois representation rho on the left-hand side is sent to a representation of the group GLN by pi of rho. I denote this by pi of rho, even though we don't know it exists in most cases. Okay, so hopefully this is not, maybe I should have put a question mark into it, but there are some things that are known. So when n is equal to 1, there's a kind of easy way to construct or to know that this there is such a correspondence in both settings, p-adic and mod p, basically because when n is equal to 1, GL1 is a commutative abelian group. So we only really care about the abelianization of this Galois group. And this is basically almost the same as GL1 of QP. So in this case, it's like in Gauss's cyclotomic story. We kind of have an isomorphism between the Galois group, roughly speaking, and the GL1 group. And therefore, if the groups are the same, the representations are the same. So there's an easy answer when n is equal to 1 that I want to mention for completeness. But then when n is equal to 2, it's a completely new, it was completely new thing to study. And there was a lot of activity, and many hundreds of pages were written by starting with Breuil, and then especially Colmez, and also Kisin, Mark Kisin, Matthew Emerton, and Vytautas Paškūnas. So in the period of 2000 to 2010, they worked very intensively on that and found there's a beautiful answer. There really is a very natural kind of correspondence when n is equal to 2 in this p-adic or mod p setting. And it also allowed them to prove something, at least special cases, many special cases of a big conjecture called the Fontaine-Mesa conjecture, which is of a similar, it's a big generalization in a way of the Shimura-Taniyama conjecture. It's talking about modularity of Galois representations. So this is for two-dimensional representations. In the remainder of the talk, I will still talk about two-dimensional representations, but there's something very interesting that happens now, namely, usually it doesn't matter too much in the classical Langlands correspondence if we replace Q or QP by finite extension, but here something really changes. In the case of GL2QP, so down here, Breuil was able to construct the mod P correspondence by hand. He kind of classified both sides. Roughly speaking, I'm oversimplifying slightly, but essentially he classified both sides and then matched them by hand. There was kind of a natural way to pair them up. I mean, I don't literally mean all representations on this side. I mean, essentially just irreducible representations, but not quite. So Breuil was able to do that for GL2QP, but something very interesting happens when we replace the field QP by a finite extension of QP. so a finite field extension of QP. Namely, we can ask the same question. It's very natural in the classical Langlands program. It doesn't usually matter whether F is QP or a finite extension, but here it does. Namely, the left-hand side doesn't really change too much when you classify these Galois representations. It does change a little bit, but not in any essential way. Whereas the right-hand side becomes a huge deal more complicated when F is not equal to QP. And this was first realized in the work of Florian around 2000 and starting around 2006, 2007. What they realized is even if you study the irreducible objects of irreducible representations of GL2F over the field FP, they become perhaps unclassifiable. I mean, they constructed huge infinite families of such representations. And later on, there was other work done by Schran and by Wu, who showed that these many kinds of representations on this side cannot be written down with a finite presentation. You cannot easily specify them using a finite amount of data. And at the moment, like I mentioned, we don't know how to construct such a correspondence by hand, unlike the GL2QP setting. I forgot to say that, I mean, these finite extension of QP arise, one important way in which they arise is when you start from a finite extension of the rationals, like the Gaussian numbers that are Qi, where I is the square root of -1, by taking the completion at any periodic absolute value. So in the same way as QP arises from Q, these extensions arise from a finite extension of Q by completing. So we're kind of stuck trying to do this by hand, but there's a different approach. Namely, you can, kind of like in the previous slide where I talked about the comparison of two kinds of Langlands correspondence by restriction, we can try to do a similar kind of thing here. And if we start in this global setting where we start with a finite extension of Q that I call E, that periodically has a periodic absolute value with completion F, the periodic field, then as I mentioned before for the Galois group of QP, it's just a small subgroup of the Galois group of Q. Something similar happens here. The Galois group of F is a small subgroup of the Galois group of E, a so-called decomposition group. And we can start from a global mod P Galois representation and then try to do this kind of restriction. So on the one hand, yeah, we can get a Galois representation of the Galois group of F by restriction. But on the other hand, because we're in this global setting, we have new constructions that we don't have available in the local context. And there's a natural candidate that I denote by PGL, GL for global, of R, that is defined using the Galois representation, and that has an action of, that is a representation of GL2F over FP. I will briefly outline the construction on the next page. And the hope is that even though we start with something global, it actually is of a local nature. So when it only depends on the restriction of the Galois representation to the Galois group of F. In a similar way to this restriction picture many slides ago for the Galois group of Q and the Galois group of QP. And if this is true, we can kind of define a mod P Langlands correspondence in this way, just sort of globalize the Galois representation, take the associated GL2F representation, and then take that. And the nice thing is, it's known that this is true when E is equal to Q. So in that case, where we do know the periodic Langlands or mod P Langlands correspondence, it really works. This hope is true. And it was proved by Emerton a little while ago. And just briefly, I'm also starting to run out of time. The idea for the global construction is that there's a geometry you can use. There's a tower of curves, maybe Shimura curves in this setting, that have an action of GL2F. And when we take a suitable cohomology group of these curves, étale cohomology groups, we also get an action of the Galois group of E, of that extension of Q. And these two actions by construction commute. And so we can use one action to narrow down, to cut down the representation and get this PGL of R. So I basically start with the two-dimensional Galois representation of the Galois group of E, the global field, and I take the homomorphism of this two-dimensional representation into this huge representation that I call H1. Since the two actions commute, I still get an action of GL2F, and I can take this as a candidate representation for what I would like to see in the mod P local Langlands correspondence. Okay, maybe just as a quick aside, how we might construct this candidate. But now, in the remaining 5 minutes of my talk, I just want to give some evidence for this hope. So the hope is that this globally defined representation only really depends on the local representation, on the one restricted to the p-adic field. And the first evidence I want to show you is that, I restrict to the simplest setting of a p-adic field, which is called unramified. Don't worry too much if you don't know what that is. And I let OF be the analog of ZP. It's the elements in F that have absolute value less than or equal to 1. Because this is ultrametric, we have an ultrametric absolute value. This is really a subring, and it's even compact. This is like the analog of ZP. And then I can look at the subgroups of GL2F that are the integer valued matrices, GL2OF, and the ones that are integer valued and also congruent to 1 modulo the identity. And then what I get, so remember, we would like that the global representation PGL of R only depends on rho, but these two results show at least a small piece of this PGL of R only depends on rho, only depends on the restriction. Namely, in the first case, it's the irreducible K subrepresentation. So we restrict this representation of GL2F to this smaller compact subgroup GL2OF. And these irreducible subrepresentations, they're actually just finite dimensional, whereas this PGL of R is typically infinite dimensional and difficult to understand. So we just understand some maybe tiny pieces of this representation, but at least those satisfy the hope. They are only depend on the local Galois representation rho. And this is something important called the weight part of Serre's modularity conjecture, which was conjectured in this precise form by Buzzard, Diamond, and Jarvis in the early 2000s, and then proved a few years later by G. Leo Savitt and G. Kizin. And then the second statement takes it further, but it's still just a small finite dimensional piece of this representation PGL of R. It's looking at the K1 invariance. The K1 invariance, where K1 is the first congruent subgroup, the one of matrices congruent to 1 modulo the identity. These only depend on rho. This is a subspace, actually even subrepresentation. And this was done by Emerton G. Savitt, Lee, Mora, Schran, and Hu, Wang, and Lee. So there were many people involved. And finally, the recent work that I was involved in, that I want to talk about, is work I did with Breu, Hu, Mora, and Schran, where firstly we showed two things that about this globally defined representation that only depend on rho. The first is that we computed a kind of natural measure of the size of this representation. It's defined in this very complicated way using a tower of algebraic curves and a global Galois representation. So it's really not easy to understand this in more concrete ways. Like we cannot easily do computer calculations. We cannot easily write down elements in it. But what we showed was the Gelfand-Kirillov dimension is equal to the field degree of F over QP. And what is the Gelfand-Kirillov dimension? One way of saying what it is, it's a kind of generalization of, if you like, a generalization of dimension to a non-commutative context. Here the group is non-commutative, GL2 of F is non-commutative. So if you do non-commutative algebra, you may come across Gelfand-Kirillov dimension, but concretely it measures how the dimension of the invariance under deeper and deeper congruent subgroups grows. So when I take smaller and smaller congruent subgroups, the space of invariance becomes bigger and bigger. They are all finite dimensional, and the growth rate is governed by the Gelfand-Kirillov dimension. It's easy to get a lower bound that was known before, and then we established an upper bound and got the answer that was expected before us. And then the second result I want to mention is kind of the first result about not just the restriction of the representation to some small compact subgroup, but really about the entire representation. Namely, we showed that this representation is close to being irreducible. It's not always irreducible, but when the local Galois representation rho, the restricted one, is irreducible, the GL2F representation is irreducible, first of all. It's so-called supersingular, don't worry too much about the term. And then the second case is when rho is not irreducible, then, typo, then by pi I mean the same thing as in the previous line. I mean the global representation is not irreducible, but it has length between 3 and F plus 1. And F plus 1 is the expected actual number. So we expect that in the second case, in the reducible case, this pi global of R is not irreducible, but it's built out of just F plus 1 irreducible objects. And we got close. We got it's between 3 and F plus 1. So when F is equal to 2, we know it's exactly F plus 1. The final small comment, I'm getting to the end of I'm maybe past my time. Maybe surprisingly, the first theorem is used to establish the second theorem. I mean, maybe not directly as it is stated in some more algebraic form. We use the first theorem to allow us to get to the second theorem. It still required a lot of work. And then a key input in the first theorem, as also in the results I mentioned on the previous slide, on the weight part of Serre's conjecture, the Taylor-Wiles method plays a very important role to get this Gelfand-Kirillov dimension. So I will stop here.
Are there any questions or comments?
Okay, so can you explain in your previous slides, you have some that commutative diagram until the correspondence of the commutative diagram?
Oh, you mean local?
Yeah, this one.
Yeah.
Yeah, so typically for I mean for this local correspondence.
At the bottom, yes.
Yeah, like a global correspondence, you can identify L functions, so you know that these two things correspond, right? So and if you just look at a local representation, and in the case that you have some ramification, you don't have Zatorski parameters, or is there any intuitive quantity that you know that these two representation corresponds?
Well, there are still some invariants you can put on both sides, and they match each other. But it's not, I mean, you're correct that in a global setting, these two sides can be matched by, for example, an L function, something that generalizes classical zeta functions. That's not as easy in the second line, in the local line. Yeah, I could have said more about this maybe. So there are invariants on both sides that still match, but it's not easy to uniquely specify the correspondence in this way. There are some characterizations that are known, but they are complicated, and they don't just use maybe 2, but they use all n at the same time in an inductive way. So there are still L series and epsilon factors and things like that you can attach to both sides, but it's not enough to uniquely characterize the correspondence. The good thing is the top line is extremely rigid, like the global setting is much more rigid. And if you, for the global setting, it's enough to verify it. I mean, as you know, it's enough to verify it like almost everywhere locally. And so here we have more freedom maybe to on both sides. On the global setting, it's much more rigid and it's easier to match. Yeah.
Can I ask a second question?
Yeah.
So can you say more about the construction of this capital pi that you mentioned, like?
Yes, I think I can say a little bit more.
Yes.
I mean, maybe this is a technical part, but yeah. So I mean, maybe the easiest to talk about is when we just take A equals Q, then we can take classical modular curves. So those are moduli spaces of elliptic curves with some fixed level structure and certain level structure. And the tower I refer to is we take increasing level structure at P. So you have P power level structure, full P power level structure for any fixed K, and then you let K go to infinity. So you have like modular curve of level 1, modular curve of level P, modular curve of full level P squared, and so on. So these form a tower. And then the GL2, the GL2 action comes from the action on the level structure. And to get the GL2, I mean, on each fixed modular curve, you get an action of GL2 Z mod P to the NZ, or P to the KZ. These are all compatible. In the limit, you get GL2 ZP, but you even get GL2 of QP when you take the whole tower and not just each individual curve. And then this, of course, comes from the cohomology theory, from the Étale cohomology. You can do the same thing. For this, it's actually not important that you take FP coefficients. You could take L-adic coefficients, or this just plays an auxiliary role. It just gives us a way to get the vector space associated to the algebraic curve.
So as a generalization, like if this is go to the high dimensional Galois representation, do you replace that to H2, H3 or something like?
Yes, you would then maybe take some suitable locally symmetric space or Shimura variety. Yes, maybe you could, for example, for GLN, one common thing is to take a unitary group setting, globally unitary, but locally at P it's GLN. And
any other questions or comments? So I have some questions. So this pi, this red stuff on this slide, is a representation of GL2F.
yes.
That's p-adic or mod P.
Here it is mod P, but you could do the same thing p-adically too. The only thing is you would not just take standard cohomology, that would give you maybe something smooth, but you would have to p-adically complete it as well.
So for this, like this is part of some category of representations. Like, how well do you understand this category? So in particular, do you understand in general, you have this idea of maybe supercuspidal representation, and you have this theory of constructing all irreducibles from supercuspidals and then classifying supercuspidals.
Okay, I can say more about that. So so this is something I studied also some years ago. So in the mod P setting, so when you study p-adic groups acting on a mod P vector space, then it is still natural, as you say, to study the irreducibles, and there's still a notion of supercuspidal. And basically, in maybe 15 years ago or so, I did establish a classification similar to Bertrand-Selewinsky classification. So how to build a general irreducible representation out of the supercuspidals. But on the other hand, we don't know the supercuspidals. Like for more classical representation theory of GLN over a complex vector space, by now we know how to classify all the supercuspidals. It's complicated, but it's completely known for GLN or even some classical groups. But in this mod P setting, as I was trying to allude to in an earlier slide, it does get much more complicated. It seems there's maybe it's some kind of wild problem to classify. I don't know.
I see.
In the sense of representation theory, but
Can you classify unramified or thinly ramified?
no.
Not even that.
I mean, I don't know what you want to be unramified, but even if you take F to be unramified, it seems to be very
No, I mean
complicated. I mean the representation.
Representation with k-fixed vectors.
But I think the notion of unramified is not exactly a good one anymore. In characteristic P, because so K1, this first congruent subgroup is a pro-P group. It's a P group. So if it always has fixed vectors on any representation. So kind of, we shouldn't define unramified or thinly ramified in the same way as in characteristic 0. So maybe we don't have a good analog of that at the moment.
Okay.
Yeah. There are some weirder things that happen in characteristic P, but I mean, the good thing is there are still some good analogies like supercaspidal and parabolic induction, and yeah. But in terms of the category theory, I think it's a lot less well understood. Like in characteristic 0, you have things like Bernstein decomposition of the category and so on. Everything is less well understood in characteristic P or periodically.
Any other questions or comments? One last question. What happens if you work instead of Q with a function field?
That's a very good question. So yeah, in number theory, you can always ask about replacing Q by FP parenthesis T, like a function field of or a finite extension, a function field of a curve over a finite field of characteristic P. I don't know anything. I mean, I know almost nothing in that context about the mod P representation theory, unfortunately. If you use the same P on both sides, I think it seems difficult. I mean, there are some purely local results that still work. For example, I think the construction, what Brian Pashkunas did, the way they constructed so many representations, it's kind of strange from the point of view of classical representation theory. To construct their representations, they use that GL2 acts on a Breuer-Titz tree, and that gives you an amalgam presentation of GL2. And then so in other words, to give a GL2 representation is the same as to give a vector space with a compatible action of two compact or compact mod center subgroups. Because it's an amalgam, you just need to give a representation of an amalgam. It just means you need to give a representation of two different group actions that agree on the overlap. And they found a kind of ingenious way to do that. And I think this even works in a function field setting. But I don't know what one would hope in that situation. Yeah.
Okay, great. Okay, let's thank the speaker again for a great talk.